All right, so last time we got into chapter 5, and we're basically talking about naming and nomenclature, and we talked basically about three types of naming. We talked about ionic compound naming, and remember, as we talked about with the bonding chapter, ionics always a metal and a non-metal together, and you always pretty much know it's going to be an ionic compound when those two things come together, based on those periodic trends that we talked about in a previous chapter. And what always happens in this case, again, is that transfer of electrons from our metal to our non-metal. And that's, again, as we talked about, what creates our ions in this case, a complete transfer of electrons. We get our positive ion, which is our cation. We get our negative ion, which is our anion. And again, it's a sort of opposite attraction there that holds that together. Now, in terms of naming, there's kind of two types of ionic compounds that we sort of classify, and they are sometimes classified as type 1 and a type 2. And really, as we talked about, whenever a sort of metal is involved in naming, it really is sort of the most important thing to look at. And that's really where type 1 and type 2 sort of come into play. And it really has to do with the metal. And in a type 1 compound, the metal has a fixed positive charge. And as we talked about last time, essentially, if you look at the periodic table, that's going to be any metal that comes from basically group 1, group 2, group 3, which is typically aluminum. That's going to be your zinc, your cadmium, or your silver. So as soon as you sort of see any one of those metals sort of involved, you know it's a type 1 situation. And really, with a type 1 metal, we don't have to do any extra work with it. We just basically use the whole name of it. And with a type 1 ionic compound, we do the whole name, basically the metal. And like most naming, our non-metal will lose the last part of the name and take the IDE sort of treatment at the end. Again, that's really all you have to do with a type 1. A type 2, on the other hand, is basically a metal that can have a variable positive charge. And that essentially is, if you look at the periodic table, that's essentially going to be your transition metals. So that's typically your transition metals, obviously, except for, the zinc, the cadmium, and the silver here. But your transition metals are typically the ones who can do that. Also, where that staircase comes down, there are some metals just to the right of the transition metals, kind of on the bottom side of the staircase. There are lead is, tin, and in that general area, there are also metals, and they can have variable charges. Now, because they can have variable charges, we do have to do an additional thing with the name, which is we still use our whole name of the metal. We still do our non-metal with the IDE sort of treatment at the end. The additional thing that we do in between is a Roman numeral. And the Roman numeral, again, indicates the positive charge on the metal. It is not, again, how many you have of the metal or anything like that. It is, if you just took one of the positively charged metals out, what the positive charge would be, and that's what we do. So in the case of, like we saw, FeCl3, we will always know the charge of what's attached to it. So here, iron, there's only one. And Cl is group 7, which means it does have a -1 charge. So there's 3 of them, gives you a -3 overall. And that's going to tell us that to balance it out to 0, which always in an ionic compound, when you take the positive guy and negative guy together, it does need to equal 0. Then that will tell us the charge. So this again would be iron Roman numeral 3. Once again for the charge. Thank you. And chloride here for the ending. Remember, the other main important thing that we talked about is we do not use prefixes when metals are involved. Yeah, so again, you should never really be using a prefix or anything like that. It doesn't matter in this case that we have 3 of the Cls. It has no effect on the naming or anything like that. The sort of third type of naming that we talked about was really more covalent bonding, where we're going to share electrons. and that's usually when two nonmetals get together. And because they're going to share electrons here, we're not going to get any ions that are going to be formed. And we basically do use prefixes here. So again, mono meaning one, di meaning two, tri meaning three, tetra meaning four, and so forth, penta, hexa, hepta, octa, and so forth. Now, there's a couple of rules about the prefixes. Pretty much, we do not use mono on the first name. But it is okay on the second. And remember that every so often you can get kind of weird spelling because of the vowel that ends the prefix and the vowel that starts the sort of letter of the element name. So typical ones that we usually want to avoid is like when we get an A and an O, A from the prefix, O from the element. We do typically get rid of the A off of the prefix. A couple of O's, again, O off of the prefix. We typically drop it. I think we looked at CO, which was again carbon monoxide, not carbon monoxide or anything like that. So again, we do drop those kind of awkward things. And in terms of naming, we go pretty much prefix on the first name if needed. And then we do use the whole name of the first element. And then we go prefix on the second name. And the second name, pretty much like everything else, will get sort of that IDE treatment at the end of it. Again, as I mentioned, I think these are really the sort of easiest ones to do, but they really are the ones that people do sort of screw up on a lot, again, because they want to do all kinds of weird things. Usually at no point are you sort of comboing these things together. So as I mentioned before, it's probably not a great idea, and you're probably doing it wrong if you're rolling with a Roman numeral and a prefix together. Again, they typically do not go together. Any questions on that naming stuff there? Okay, we got a couple more naming stuff to talk about. The next thing we're going to talk about is how we go about naming polyatomic ions. And polyatomic ions are really groups of nonmetals together that actually are sharing electrons, but because of the way they're sharing electrons overall, they do actually end up with a overall positive or overall negative charge. So they are ions, and they're kind of interesting things. They're ions overall, but they are technically still sharing electrons because it is nonmetals and nonmetals coming together. So if we take a look at this example here, which is NH4NO3, this is actually two different polyatomic ions together. And if we were to break this sort of guy up, it would be a break up right about there. And we have one polyatomic ion, which is NH4Na plus. And that one nitrogen and those four hydrogens are all staying together. They're all held together by sharing of electrons. Overall, it has only a +1 charge. If you take a look at the NO3 on this side, that is NO3 minus. That one nitrogen and three oxygens are also sharing electrons and staying together. And the overall unit there has a -1 charge. So a couple of things on this. This is really an ionic compound, so the same rules follow as we talked about with our original ionic compound, which is positive and negative when you put them together does need to equal 0. So even when you got a polyatomic ion involved, when you put things together, again, it does need to equal 0. And that's why when we look at the formula here, that's basically +1 and -1. So when we do put it together to make this formula, we really only need one of each. And again, that gives us an overall charge of 0, just like we did with type 1 and type 2 sort of compounds. Now, each of these actually have a specific name that goes with them. So NH4 plus, which is one of the few positive polyatomic ions that you come across, Most polyatomic ions are negatively charged. There are a few positive ones, and this is probably the most common positive one that you will see. This is our friend, the ammonium, not ammonia, but the ammonium ion. Not to be confused with ammonia, which is NH3 no charge. This is NH4 plus, obviously with a plus one charge, which is an ion. Over here, NO3 minus is our friend nitrate ion. And one of the good things about polyatomic ions, if you could say there's good things, is we basically just use the name. So it doesn't matter how many of them you have. The polyatomic ion, whatever its name is, it's its name. So if we were going to name this guy here, we would use the name of the first one, which in this case would be ammonium. And we use the name of the second polyatomic ion, which is nitrate. And NH4NO3 is ammonium nitrate. And again, like I said, it doesn't matter if you have multiples of the polyatomic ions. It does not affect the name. We just use the actual name for it. First off, any questions on that? By the way, we did actually draw both of these, I think, when we were in chapter 12 and we talked about bonding. So again, what we're really looking at here is NH4 plus, which looks like this. I believe we drew this Lewis structure. And we had NO3 minus, which has a double bond. And again, ionic compound plus one and minus one coming together. Again, basically something that is sharing electrons, but overall does end up with sort of a positive or negative charge in this case. Any questions on that there? Now, because as I mentioned, there is, I would say, more negatively charged polyatomic ions than positively charged polyatomic ions, I would say in most cases, you probably won't have two polyatomic ions together like we see here in most cases. So in most cases, since most of them are negatively charged, what typically happens is they find themselves with a metal a lot of times. So you very often find a metal and a polyatomic ion coming together, and the metal plus the polyatomic ion is probably typically what you will come across. Now, because the metal is still a metal, it is the one that's going to make your cation that's going to be positively charged. And obviously, our polyatomic ion in most cases will be our anion that is negatively charged. And because they typically will hook up with a metal, what that means is same rules apply. The metal is always the most important thing. So, for example, if we take a look at Fe NO3 2 and maybe NaNO3. We'll take a look at that. So when we look at each of these here, what we end up with is, in both cases, a metal and a polyatomic ion. We'll start over here on the right. So that is a metal, which is sodium, and that is our polyatomic ion, which is, as we just saw a second ago, nitrate. So when we look at this, really, whenever you have that metal, as I mentioned, it's really the thing that you want to look at. So when we see Na, which is sodium, we go to the periodic table. We see sodium is a group number 1, which tells us it is a type 1 metal. It has a fixed positive charge. It will be plus 1 no matter what the situation is. So basically, that sodium is plus 1. And that nitrate, which again is our polyatomic ion, altogether is minus 1. And once again, that is why the formula, as we see above, is NaNO3, because ultimately we're putting together plus 1 and minus 1. So we just need one of each of those. Now, the important part is the metal, and because that is a type 1 metal, we just simply use the name of the metal, which is sodium. And again, we use the name of the polyatomic ion, which is nitrate, and that NaNO3 would be sodium nitrate. Any questions on that there? Now, if we take a peek over here on the left, and we would break it apart right about there, we once again see a metal And we see our polyatomic ion. And unlike this metal here, that is a type 1 metal, once again, the metal is the most important thing, and iron is a type 2 metal because it is sitting again in the transition metal region. And that again tells us that we should use a Roman numeral in this case, and we need to figure out the charge of the iron. And just like we did previously with type 2, although we may not know what the charge is on the iron right off the bat, we will know what the charge is in this case of the polyatomic ion, and that is NO3 minus. But once again, there's not just one of them, there's parentheses in A2, which implies that there are two of these polyatomic ions. And that gives you a -1, and a -1 is a -2 overall. Once again, that would tell us in this particular case, our iron is +2 to balance it out to 0. And because iron, again, is a transition metal or one that could have a variable charge, a type 2 metal, we will go with our iron, once again, Roman numeral 2 because of the charge. And again, even though there are multiples of the polyatomic ion, it has no effect on the name. This is going to be nitrate. So this is iron 2 nitrate. Iron with the +2 charge is our cation in this case, and the nitrate with a -1 charge is our anion. Any questions on that? So I would say probably 99 times out of 100, this is probably what you're going to end up with, which is a metal and a polyatomic ion. So again, what you want to kind of do is just default back to the type 1, type 2 rules, and really just decide based on the metal, do I need a Roman numeral or not? And that's basically all I have to do. The other really important thing is, as you can see here in this particular formula, we have 1 iron, 2 ion, and we have 2 nitrates. And when we do put that together, we do get 0, but we do need to write the formula correctly. And if I wrote it like this would be incorrect because basically I'm saying I have 32 oxygens, which clearly I do not. So whenever you have more than one polyatomic ion, you always have to put parentheses around the polyatomic ion and then the number on the bottom of the parentheses to indicate how many you have. So that's one thing with polyatomic ions is, again, if you have more than one of them, you do need to put parentheses around it when you're writing the formula and put the number on the bottom to indicate how many. Any questions on that there? All right. So here's a table of some polyatomic ions, and obviously at this school you need to know everything. Here's a more organized table by charges, whichever way you want to look at it. But let's talk about some of the things that we can sort of learn, and you do need to learn obviously the names and the formulas that go with it. And you need to know, obviously, with the formulas, the proper charges so you can put things together properly to balance it out to 0. So, for example, if we look at some of the ones on here, if we look at like NO3 minus, which again is 1 nitrogen, 3 oxygens, and NO2 minus, which is 1 nitrogen and 2 oxygens. NO3 minus is, as we just saw there, the nitrate, ATE. The NO2 minus is what is known as the nitrite ion, ITE. If you take a look at SO4 2 minus, that is sulfate. And if you take a look at SO3 2 minus, that is sulfite. So when you look at some polyatomic ions, and sometimes people group them up by groups of 2 or groups of 4. If you take 2 guys that are related to each other, and both of these guys are related to each other, if you take a look at each of these, for example here, this is 1 nitrogen and 3 oxygens with a -1 charge. That's 1 nitrogen and 2 oxygens with a -1 charge. The only difference between them is the number of oxygens. And what we see is the one with the most oxygens ends in 8. The one with the least oxygens ends in 8. That also works up here for our sulfate and sulfite. This is one sulfur with 3 oxygens and a -2 charge. That is 4 oxygens and 1 sulfur with a -2 charge. And once again, only difference here is 1 oxygen. Everything else is exactly the same. The charged, the main guy as well. Again, the one with the least number of oxygens will end with "ite." The one with the most number of oxygens will end with "ate." So that's a really good way to sort of organize these and learn these. Is you could do it one of two ways. You could just either memorize everything individually if you want, or what you could do, for example, is memorize all the eights and know if you need an "ite," it's just 1 oxygen less, right? You just had to drop an oxygen basically to do so. You will also see some other things on this table. So, for example, if we take a look at a very common sort of 4-pack that is related to each other, we have, and it's right about here, I think, ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. Every single one of these all have a -1 charge. The absolute only difference between all of these things is the number of oxygens. They all have chlorine in there, and they all have different numbers of oxygens. So when you do have a group of 4 that are related to each other, we kind of work it the same way. So in a group of 4, we could kind of break it right about there. Now everything to the right of my line has the least number of oxygens. So again, because it has the least number of oxygens, ITE is what they should end with. Again, those with the most oxygens is ATE, like you ate too much is a good way to remember that. So if you ate too much, you're going to be on the left-hand side here. We have ITE. So this will be chlorite, ITE. This guy at the end, ClO minus, will be chlorite as well. You obviously cannot have the same name for 2 different things. So what happens in a group of 4, the one with the least number of oxygens in that group of 4 will end with ITE, but will also start with hypo, like less than. Yeah, this is basically what hypo means. So ClO minus is hypochlorite. ClO2 minus is chlorite. Now, if we go to the left, we have the most oxygens, which should end in "ate." So this is going to be chlorate. This is going to also be chlorate. Once again, we cannot have 2 things that have the same name. So in a group of 4, the one that has the most oxygens will end in "ate," but will also start with "per." So that is perchlorate, chlorate, chlorite, and hypochlorite. And that is a group of 4, a very common group of 4. By the way, that is a group of 4 that contains the halogen, right? Cl, which is a halogen, which means you can swap out that halogen for some other halogen like BrO3 minus. Now, if you had to take a guess, instead of chlorate, BrO3 minus would not be called chlorate, but it would be called bromate, yeah, because it has bromine in it rather than chlorine. So this would be bromate. If you swapped it out for an iodine, instead of bromate or chlorate, this would be iodate for iodine. So with those kind of groups of 4, you could actually swap it out, anybody in the halogen there, and it's basically kind of named the same way along the way. So like I mentioned before, a really good way to kind of learn these is just to learn how to adjust things, so that you can maybe just learn one of the names and know how to kind of move up or down. And when you're moving up and down, you're really just moving the number of oxygens either up or down. Everything else stays the same. Other things that you also commonly will see, as you can see here, this right here is CO3 2 minus, which is carbonate. And if I put an H plus in front of carbonate and join those guys together, I get HCO3 minus. And once again, the hydrogen and carbon and 3 oxygens also together has a -1 charge. Basically, all I did was put a hydrogen on in front of that, and that is why this is called hydrogen carbonate, because I added an H plus. By the way, I did not just add an H, I did add an H plus, which changes the charge. You can see carbonate goes from -2 to -1 because I basically have -2 and +1, leaves you a -1 left over, so the charge changes. By the way, hydrogen carbonate is very commonly referred to as bicarbonate, exactly. And that is definitely a very common name that is still used today. So you should know both for that one. Bicarbonate is hydrogen carbonate. And also for sulfate as well. That's also a very common one as well. Same deal. You could put a hydrogen in front of sulfate and you get hydrogen sulfate. And that's also referred to as bisulfate. So sometimes they will use bi instead of hydrogen in those names. And again, those two names are still very commonly sort of used. So you should be familiar with both of them. Now, as I mentioned before, uh, you will never use a prefix and a Roman numeral together. The one exception where this could happen is if you have a polyatomic ion. So, for example, if you put a metal together with dichromate, we are not really putting a prefix in this name, but the name of the polyatomic ion has a prefix in it. And that's the only case where you could have a Roman numeral and a prefix together. And that's really because you're not really putting the prefix in the name. It's actually just part of the actual name of the compound itself. Other than that, you shouldn't really, again, have Roman numerals or prefixes together. So, like I said before, it's a really good way to remember it. It's just to know how to adjust it. So, if I had PO4 3 minus, which is phosphate, AT, and I needed phosphite, it should have one less oxygen. So the only thing that should change is just drop one oxygen. Everything else stays the same. And now I have phosphite, right? And if I wanted hypophosphite, technically I should drop one more oxygen off of that, yeah? And you could go down to like PO2 2 minus, or 3 minus, oops, sorry, 3 minus on those. And you'd end up with hypophosphite. So it's a really good way to remember these again, just to kind of know how to adjust. And if it's something that can be a group of four, again, all you're doing is just changing the oxygen. And that's, like I said, the best way to sort of put these together. Now, although a majority of all polyatomic ions will end in either ate or ite, there are some polyatomic ions that actually end in IDE, kind of like what you find on the periodic table. So some common ones that sort of end on the IDE that you do come across. Again, we should have hydroxide, IDE. We also have cyanide, IDE. We have azide as well. So there are a few polyatomic ions that will end in IDE, but a vast majority that end in IDE should be something from the periodic table. But there are, again, a few that are polyatomic ions that will do it in that way. 8 and I should definitely be a polyatomic ion, and sometimes people get all those things confused. So try to think about sort of the names. Any questions on that there? So let's try some here. Let's go with, we'll leave this chart up here. Let's do some names here. So let's do. Then let's do some formulas. Let's do ammonium sulfide. Let's do iron 3 perchlorate. And do some sodium. Okay, so let's take a look, see how you're doing here. So I come over here to this page. All right, so first thing to recognize, obviously, is we definitely have a polyatomic ion right about there. And we do have a metal. So once again, the metal can kind of determine, and we see the metal is calcium, which is group number 2, and has a fixed positive charge. So that's a type 1 metal. So we really just need to basically use calcium, as there's nothing else needed. Here we do want to identify our polyatomic ion. Once again, that is HCO3 minus. And this is really calcium with a +2 charge. This is why our polyatomic ion does have parentheses around it and a 2, because we need not 1, but we do need those 2 of them to balance out that +2 charge. That is hydrogen carbonate or bicarbonate, whichever way you want to use it. And putting those together here, we don't need any Roman numeral with our calcium. And again, it doesn't matter how many we have of our polyatomic ion, it's just going to be the name. So calcium hydrogen carbonate, or again, it could be calcium bicarbonate if you want to go that route as well. Any questions on that one there? Here again, we split it and we do see a metal and we do see a polyatomic ion. Our polyatomic ion here is OH minus, which once again, if you memorize and go to your table there, you will see is hydroxide, one of those few polyatomic ions that do end in IDE. That means, though, when we look at the metal, our metal is copper, which is a type 2 metal, transition metal. That means we do need a Roman numeral here. So we do want to figure out what the charge is. And once again, knowing that this guy is -1, in this case, it will be copper with a +1 charge to balance it out to 0, because again, it's ions and we do want it to equal 0. So now we got everything we need for the name. So whole name of the metal, copper. We're going to Roman numeral 1 for the charge on the copper. And again, we're going to use the whole name here of our polyatomic ion, which is hydroxide. Yeah. So copper, Roman numeral 1, hydroxide. Any questions on that one there? Lastly, polyatomic ion right there, and a metal, which is nickel. And again, our polyatomic ion is PO4, which is phosphate down there at the bottom. And maybe we'll be able to see it here on this one here. Phosphates right there. Over there. And we'll go with PO4 3 minus. Once again, nickel is a transition metal, so we are not sure the charge of it. In this case, though, we do have 3 nickels, not just 1. And we actually have 4 of the phosphates in this case. Squeeze one up here, maybe. So that's -3, 6, 9, and 12. So each one is, we got -12 overall. We do have 3 of the nickels. That means each nickel would be +4 in this case, right? +4, +8, +12. So our nickel here individually would have a +4 charge. That will translate into, I'll just go underneath it, nickel Roman numeral 4. Once again, because of the +4, not the grand total. And again, we're just going to use the whole name there of phosphate, ATE, for our polyatomic ion. Any questions on any of those names there? All right, if we were given the formula, we again just kind of work backwards, and much like what we did previously, in this case, we do see ammonium, which tells us it's a polyatomic ion. Sulfide, so we do know it's an ionic compound. So we once again just want the basic units that make these up, the basic ions. So ammonium, once again, is NH4 plus, with again a +1 charge. Sulfide, IDE, is actually sulfur from the periodic table, so that is group 6 there. Again, that is not sulfate, that is not sulfite. This is sulfide, IDE, periodic table. So we do want to put it together. So we're basically taking a -2, putting it together with a +1. And in this case, we actually need one more of our positive guys here. That gives us a +2 to balance out the -2. And now we can write our formula. We have 1 and 2 of our polyatomic ions. Because it is more than 1, we do need a parentheses with the number on the bottom to indicate that there's 2 NH4 pluses. And we obviously have just one of these guys, so a little S, and we're good to go in this case. Yeah. Any questions on that formula there? Next, we have iron 3 perchlorate. Once again, iron 3 tells us we have an iron with a +3 charge. That again is what the Roman numeral means. Perchlorate is one of those group of 4s. So maybe, you remembered ClO3 minus, which is chlorate. So perchlorate would have one more oxygen. So ClO4 minus would be perchlorate. Yeah. So here we're putting together +3 and -1. So in this particular case, we actually need 3 of the perchlorates to balance it out. And what that looks like is we will again need a not Roman numeral, but we'll need a parentheses to put our perchlorate in. And once again, we will put the 3 on the bottom. You won't put the charge in like I did, just it's automatically writing charges. There we go. Get rid of the charge. There we go. As we go there. Any questions on that one there? All right, so lastly here in terms of a name or a formula, we have nickel, we got sodium oxalate in this case. So sodium is group 1, has a +1 charge. Oxalate is C2O42 minus. So once again, we are putting together really a -2 with a +1. So we do need an extra +1 there to balance it out. That's going to give us a +2 to balance out the -2 in this case. And we have 1 and 2 sodiums, so Na2, and only one oxalate here, C2O4. Once again, if you have just one polyatomic ion, you don't need parentheses around it. It's just when you have more than one. Any questions on polyatomic ions? So obviously they want you to memorize everything, so we'll roll with this table. Yeah, what's on this table you're responsible for. Yeah. Any questions on polyatomic ions or how to handle them? And again, it's the best way I really do think is just to kind of memorize either the eights, the i's, and again, just know how to adjust up or down. Makes it a lot easier than maybe just trying to remember everybody individually and stuff like that. All right. Here are some of those patterns we talked about. Again, a group of 4. We'll begin with per for the most oxygen and with hypo for the least. And as I mentioned, you could swap it out, that halogen, for somebody else, and you'll get a similar name. And again, if we put hydrogen in front of something, it does affect the overall charge because it's H plus being added, not just a hydrogen, but we do just basically call it hydrogen. All right. And again, these are the ones we just talked about. So the last thing we're going to talk about is naming acids. And an acid is a substance that has the ability to basically produce H plus ions or hydrogen ions in solution, or H3O plus, which is a polyatomic ion, which is known as the hydronium ion in solution. So acids are a couple of things. First off, for an acid, because the definition is basically the ability to release H plus into solution, the cation, the positive ion for all acids is H plus. So that is basically your positive ion when you're writing a form of an acid. Because acids are in solution, you typically will see the aqueous symbol next to it. So you typically will see acids written with the aqueous AQ symbol, which basically means a water environment. Basically, you have a solution. And how we go about naming acids is really involving one important thing, whether or not there is oxygen. So if there is oxygen, you name it one way. If there is no oxygen in your acid, you name it another way. So oxygen is really important. There are certain types of acids which are sometimes referred to as oxyacids because they contain oxygen, hence they're called oxyacids in that case. So let's just talk about how you name it. So here we go. So flow chart here. We go in with our acids, and it's all about, like I said, is there oxygen, right? So it's all about whether or not there's actually oxygen there. And if the answer is no oxygen, the way that we name an acid that does not contain oxygen is it will start with hydro something ic acid. The missing part is the negative ion. So whatever it's attached to is sort of what fills in the missing part of the name. So for example, if I have HCl, this is an acid. This is basically H plus and Cl minus. So we would name it, there's obviously no oxygen involved. So this would be hydrochloric acid, again from the chloride here. So the negative guy is sort of that missing piece in that. If I had HBr, that was aqueous. This would then become hydrobromic acid, as again, there's no oxygen involved. So this would be hydrobromic acid. And again, this is H plus, which is always the cation, and this is Br minus. This is also why we have hydrogen that's basically named kind of like this and like a type 1, because for the acid component of it, it very much behaves like almost like a type 1 there. This is why, for example, if we had HCl that was in a gas phase, this is hydrogen chloride gas. Chloride, I spell it right. Chloride. Now, if you bubble that through some water, it becomes an aqueous solution, and it becomes HCl that's now aqueous, AQ, and now it becomes an acid, which is hydrochloric acid. So when you're writing formulas for acids, or you typically see a formula for acid, if they don't say in the problem, hey, this is an acid, they typically will put that little aqueous symbol next to it so you know that you're dealing with an acid rather than, say, a gas, which it would be called hydrogen chloride. Same thing with like the HBr and so forth, same idea, same situation. Any questions on that there? Now, if you do have oxygen, and the answer is yes, there is oxygen in my acid, it will most likely contain a polyatomic ion, which, as we just talked about, the polyatomic ions end in one of two ways typically. They either end in ate or ite. And if your acid does have oxygen and it does contain a polyatomic ion that ends in 8, your acid name will be something ic acid. So, for example, HNO3, that is H plus, and that is our polyatomic ion NO3 minus. This is known as nitrate, ATE. That means HNO3 would be nitric acid. So this would be nitric acid based off of that. If I had H2SO4, this again is our H, this is our SO4, that is SO4 2 minus. That is sulfate. And this would then become sulfuric acid in this case. Yeah. Now, why do I have 2 hydrogens? It's the same idea. You could think of this as an ionic compound. I have a -2 on the sulfate. I need not 1 H plus in this case, but I need 2 of them to balance out the charge. So that is why this formula here has a 2 next to the hydrogen, again, to balance out the charge to get it to 0. Lastly here, in terms of acids, if your acid does have oxygen and it contains a polyatomic ion, but that polyatomic ion is ITE ending, your acid will be something OUS acid. So if I take HNO2, H plus, NO2 is NO2 minus. Well, NO3 minus is nitrate, ATE. This is NO2 minus, which has 1 less oxygen, which means it should be nitrite, ITE. So because it's nitrite, ITE, this will become nitrous, OUS acid. Yeah. Same thing, I go H2SO3. Once again, I have my H plus. This is SO3 2 minus. That again is very similar to sulfate, but 1 oxygen less. So instead of sulfate, this guy would be sulfite. And that means that the acid name here would be sulfurous, OUS acid. Once again, here we need an extra hydrogen to balance out the -2 charge for our sulfite. So when we're naming acids, it's all about whether or not there's oxygen. If there's no oxygen, hydro to begin with, IC at the end of it. Middle part is the negative ion that's there, kind of part of his name. If it does have oxygen, it will contain a polyatomic ion, which again will either end in 8 or ite. And if it ends in 8, ic is going to be the ending. If it ends in ite, OUS. Again, a way to remember that is you ate too much, you feel icky. Yeah, so ic at the end of it is a good way to do that. They never mix, yeah, so there should be no like hydronitric acid or anything like that. That's going to get you probably an X, yeah, so don't mix those things. Hydro, again, only for ones no oxygen. If you do have oxygen, there should be no hydro in those names of the acids. Good news about bases. Most of our bases are named, a lot of them have hydroxide in them. So they're just kind of named like normal, like sodium hydroxide, potassium hydroxide, calcium hydroxide. Any questions on acid there? All right. So as you can see here, this table from your book, again, all these are acids. All these do not have oxygen. And once again, you can see they all start with hydro and end with ic. So HF would be hydrofluoric acid, HCl hydrochloric, hydrobromic hydroiodic acid, HCN hydrocyanic acid, H2S hydrosulfuric acid. So no oxygen, hydro to begin with, ic to end with, and the middle part. Here are some of our oxygen-containing ones: nitrate, nitric, nitrite, nitrous, sulfate, sulfuric, sulfite, sulfurous, PO4, phosphate, phosphoric, that's acetate, ATE, acetic acid. Yeah, so again, that is the pattern here. Again, all these have oxygen, none of them have hydro in the name, so no hydro with oxygen. All right, so obviously here, HF would be hydrofluoric acid, as we just saw. And once again, this is the one we did earlier, HNO3, again, that being nitrate, would be nitric acid. Now, let's just say, for example, you had some names like, actually, let's do this. Why don't you do this? What is the name of this guy? And let's do some names here. Let's go with, what is the formula for phosphorus acid? And let's do hydrosionic acid. Let's do chloric acid. All right, so name the top one, and then we'll do formulas for the bottom three. Let's take a look. So first, we'll start with the top one here. So obviously we have an H. This is ClO4 minus, which is a polyatomic ion. Obviously, it contains oxygen. That is perchlorate, ATE. That means that my acid name here is going to be perchloric acid. And again, in this case, the per part of the name for the polyatomic ion still stays, and that would be perchloric acid. Any questions on that one? Now, if you have the name like we do here in these examples, you could get a lot from the name to sort of help you out, maybe figure out what the formula is. The good news is if it is an acid, you already know that the cation or positive guy is H plus. So really all you have to figure out is the negative guy and then put it together to equal 0, basically. So if I look at this name here, carbonic acid, the first thing I see is there is no hydro. And because there's no hydro, I know that this contains oxygen and does have a polyatomic ion. Now, what polyatomic ion does it have? I could also get that from the name because I see it ends in ic, and I know that when my acid ends in ic, my polyatomic ion ends in 8. So literally, you could just cross out the ic here and insert the 8, and now you got something that looks like carbonate. And now you know that your negative guy is carbonate. And again, from the name, you could kind of figure that out. Now what's left is to put this together so that we equal 0. So obviously in this case, we need not one H plus, but we need 2 of them to balance. And that's going to give us a formula of H2CO3, again, with the little aqueous symbol next to it. Any questions on that? Same thing here. I come to phosphorus acid. Once again, I do not see hydro, so that tells me it has an oxygen and it's a polyatomic ion. I am now going to look at the ending. OUS means that the polyatomic ion should end in ite. So once again, you can almost just cross out the OUS and put ITE, and you get something that kind of looks like phosphite, and that hopefully should point you to phosphite. And once again, if you're not sure what phosphite's symbol is or formula, but maybe you remember that PO4 3 minus is phosphate, that would tell you that phosphite is 1 oxygen less, which looks something like that. And now we need, again, the appropriate number of H pluses to balance it out, which in this case is 3. And that will give us a formula H3PO3. That is aqueous in this case. Any questions on that? We see hydrocyanic acid. So hydro tells me this is not a polyatomic ion. There is no oxygen there. And really now I could just go to cyanic, and that sounds like maybe cyanide. And that's going to be Cn minus and H plus, and putting that together, HCN in this case here. And lastly, we see no hydro here. So that tells me polyatomic ion. I see IC, which tells me my polyatomic ion should end in 8. So if I just cross that out and kind of put 8 back in there, that looks like chlorate. And that again is going to give me the negative ion that's going to be. And once again, the positive ion is going to be H plus always. And putting them together, in this case, we actually just need one of each. We're going to get HClO3, which is chloric acid in this case. So if you have the name of the acid, again, remembering sort of the rules for acids, you can literally almost cross out the last part of the name, kind of put in the 8 or the ite, and that will point you to maybe the right polyatomic ion to use. Any questions on how to name acids? Okay. All right. I think we're good. To continue on, and we're off. And in this chapter, we're going to talk about chemical composition, like the title said. So we're going to talk about atomic mass in this chapter. We're going to talk about Avogadro's number, moles, empirical and molecular formulas. So a lot sort of bundled into this one. So let's get started, I think. So one of the things we're going to talk about is first atomic mass. And one of the fundamental properties of atoms is obviously this magnet. As we talked about, obviously atoms have protons, electrons, and neutrons. So obviously the mass of the atom is related to those and how many they have of each of those. Obviously, a atom is extremely small, so you can't just like pick it up and put it there on the balance or anything like that and weigh it. And typically speaking, when we can't sort of directly measure something, usually in chemistry or in science, oftentimes they will choose sort of a standard to compare everything to. And for atomic mass, they took an isotope of carbon and used that as the standard to compare everybody to. And it was the carbon 12 isotope. And the carbon 12 isotope has 6 protons and 6 neutrons and has a mass of exactly 12 atomic mass units, or AMU is sometimes referred to. So they basically sort of compared everybody to the mass there of this standard. And when we talk about atomic mass, again, we're talking about really the sort of bottom number that we see on the periodic table. So the bottom number there again is our atomic mass, as we talked about when we're doing mass number. It is not the mass number, but it is the atomic mass. And one of the units, for example, that we could use when we look at the periodic table and take that is we could say, for example, in hydrogen, there is 1.008 AMU in one atom of hydrogen. And again, that is one of the values that we could kind of pull from the table there. Now, atomic mass or atomic weight is sometimes referred to. Experiments have shown, for example, that hydrogen is only about 8.4% as massive as carbon 12 isotope. So just doing a simple little calculation, obviously that's 8.4% converted into a decimal, times it by the atomic mass there of our standard isotope. And again, we do end up with sort of that number that we see on the periodic table, the 1.008. Similar types of calculations were done for obviously everybody on the periodic table there. Oxygen is 16 AMU, 55.85 for iron. I will say that, as we'll talk about in this chapter, don't use AMU all that much in chemistry. We use a more useful unit, as we'll talk about later on, which is molar mass, which has to do with grams. And we don't usually use AMU all that much. Now, when you look at carbon, for example, on the periodic table, you will see the number 12.01 listed. And you may say to yourself, if they used an isotope of carbon as the standard to compare everybody to, and that isotope had a mass of 12, why does it say 12.01 up there, the periodic table? And the reason for that is what we actually see up on the periodic table is an average atomic mass. And an average atomic mass of all the naturally occurring isotopes for that particular element. Um, although most people just call it atomic mass, we don't usually call it average atomic mass, but it is the average atomic mass of all those naturally occurring isotopes. So, for example, one of the ways that we could kind of calculate the atomic mass is through this sort of formula. We could take the, or figure out the mass by basically taking the percent abundance of the first isotope. Remember, an isotope is the same element, but has a different mass, has a different number of neutrons involved, times the atomic mass of the first isotope. And then what we want to do is actually add it to the percent abundance of the second isotope times the atomic mass of the second isotope. And we would continue this pattern if we had 3 isotopes for however many isotopes we sort of had. The percent abundance, or sometimes referred to as relative abundance, is the percentage really out of 100 that this isotope appears, basically. Yeah, so bless you. So you could have, for example, 3 isotopes of an element that naturally occur, and maybe 30% of the time it's this isotope, maybe 50% of the time it's another isotope of that element, and maybe 20% of the time it's another isotope. So out of 100% of the time, that is the percent abundance. So if we take a look at carbon, for example, carbon basically has a couple of isotopes that occur, and the carbon 12 isotope and the carbon 13 isotope. The carbon 12 isotope occurs around 99% of the time, and the carbon 13 is about 1% of the time. And that's the relative abundance basically there. So that's your relative abundance percentages. And we could use that formula that we just saw. So this is basically taking our 98.89% and convert it into a decimal. We're going to multiply it by the atomic mass of the carbon 12 isotope. So right here, this is all the carbon 12. And then this is all the carbon 13 information right there, which again is 1.1% converted into a decimal, divide by 100, or move the decimal place 2 places to the left, and times it by the atomic mass there of the carbon 13 isotope, which as you can see is 13.0335 or 00335. And if you do that, you will end up with that 12.01 number that you see up there on the periodic table, which again is the average atomic mass. It's important to realize that, if you could pick up an atom of carbon, either the carbon 13 or carbon 12 isotope, you will not find one that has a mass of 12.01. You would either find the carbon 13 isotope, which obviously has a mass of about 13 and change, or you would find the carbon 12 isotope that has a mass of 12. So again, a more average value is what we sort of see on the periodic table. So why don't you try it here? Bromine 79 occurs about 50.70% of the time and has a mass of 79.92 AMU. Bromine 81 occurs about 49.32% of the time and has a mass of 80.92. Based on these numbers, calculate the atomic mass of bromine. So take a few moments there and see what you end up with. All right, let's take a look. So really one of the things you want to think about when you look at this is you want to look at the percentages real quick. Just keep a quick look at them, make sure that they do add up to 100%. are somewhere in that ballpark. They may be a little shy of 100%. They may be a little bit more than 100%. But they definitely should be in the sort of the 100% ballpark, which we do have in this case. If they are not, then you might be missing like an isotope that you might have to figure out. And obviously, if you're missing an isotope and they didn't add up to 100, I could add up all the other percentages and subtract from 100, right? And then that will give you kind of the missing percentage that would be there, assuming they're all there. So we have basically two isotopes here. We got bromine 79, which is basically rolling at 50.70%, and an atomic mass of 79.92. And we got bromine 81, which is rolling at 49.32%, and an 80.92 AMU. So we basically have our first isotope and our second isotope here. And again, we're going to figure out the atomic mass by using that formula there. I'm going to take my 50.70%. And again, you could either divide it by 100 or just move the decimal place 2 places to the left, or divide it by 100, and I'll do that for you. And we're going to times it by 79.92 AMU. Now, everybody always wants to multiply at this point, but it is adding here, so we do want to add. And same thing here. If you don't want to move the decimal point, you could take 49.32% divided by 100%, and that will do it for you. And then you can times it by 80.92 AMU. And we will end up with here, come here, calculator, point. It's like 80.43 here. Based on these numbers, would be the atomic mass of bromine. I would say, typically speaking, when we take the atomic mass, and later on when we take molar mass off the periodic table, are in general, if you're calculating any of those things, typically 4 significant figures is sort of like the general rule of how far to kind of take it. Also, usually if you're pulling a number off the periodic table there on the bottom, 4 sig figs is kind of like the general rule of how far you should take it. Depending on the periodic table you're looking at, you may have more numbers, may even have less numbers sometimes, but that's usually what you want to go with. All right, why don't you give this one a try? An isotope that is 70.5% abundant. It has an atomic mass of 117.8 AMU, while the other isotope has an abundance of 29.5% and an atomic mass of 120.85. Calculate the atomic mass here and see what you come up with. Okay, so once again here, if we take a look at our two isotopes and just kind of look at the percentages, we are there near that 100 number there, which is what we're looking for. So again, we'll take our first isotope there, which was 70.5. So again, just moving the decimal place 2 places to the left, and we're going to times it by the atomic mass of that first isotope, which is 117.80. We're going to add it to our next isotope, which has a percentage of 29.5% converted into a decimal, times it by our other isotope's atomic mass. And if we do all that good stuff there, it looks like maybe 118.7 AMU. And maybe that's 10 up there on the periodic table. Any questions on that? Yeah, so in general, and again, it depends on the periodic tables. Some will have a lot more numbers actually than just the hundreds. So the general rule is usually if you pull any of those numbers off the periodic table, which we'll do a lot coming up for molar mass, the general rule is like 4 significant figures is really what you want to go with. Yeah. Other questions? All right, so like I said, an AMU is a unit that we don't really use all that much in a lot of chemistry. We do use sort of a unit that's more useful for us, which is a gram. And you can kind of see the relationship between an AMU and grams. It's about 1.66 times 10 to the minus 24 grams in an atomic mass unit. And that's also why, as we'll see shortly, we don't really use AMU and atomic mass a lot. We use more molar mass, which has a lot to do with, again, grams in those units. But if you were going to pull some things from the periodic table, once again, you can use it as a conversion factor. So as we see there, 12.01 AMU in one atom. That will give you really your kind of two conversion factors that you could use in the calculation. 12.01 AMU in one atom of carbon, or you can flip it around and do the atom up on top. 12.01 AMU. So once again, if we want to know the mass of 431 carbon atoms, we can definitely use the AMU there from the periodic table, and we'll end up with something like 5176 in this case. Same thing with aluminum. If we take a peek at aluminum there on the periodic table, 2698, basically telling us that in one aluminum atom, there's 2698 AMU. And that's going to give us our two conversions, one like that or one that we could flip. And once again, if we want to know the sort of mass in AMU of 75 atoms of aluminum, we could do a dimensional analysis where aluminums will cancel and we'll end up with the mass there. All right. Like I said before, we really probably won't use that all that much at all. But what we definitely will use probably more is definitely molar mass. And to some extent, Avogadro's number will pop in there. Not as much as you usually think in chemistry, outside of the chapter where Avogadro's number is in. But Avogadro's number is an important sort of relationship. But molar mass really is a very important relationship that we use. And really, you should think of both of these as really nothing more than really just a conversion factor. So really, each of these are conversion factors to allow us to convert some units into more usable sort of units for things. So the first thing we're going to talk about is the mole, and not the furry guy there, but the mole is a name in chemistry that basically represents a certain amount of something. So in life, we have a lot of names that we use that actually represents a number, right? So if you say you got a dozen roses, they hopefully gave you 12. If you got a pair of shoes, you hopefully have two. If you got a gross of pencils, which I think is the only place you should use that, maybe gross some paper as well. Gross is 144 of something. So in chemistry, we do have a word that does represent a certain amount of something, and that is the mole. And the mole is actually abbreviated as MOL. So that is, by the way, the abbreviation for the mole. They had to cut something off, so they cut the E off. There's not a lot to cut off there. Now, I bring this up because it is a very common mistake that a lot of people make is when they're doing problems and they come across the mole abbreviation, MOL. A lot of people's brains automatically think molecule when they see that, yeah? And that is not what it means. It does mean moles. I would say probably almost all of the time in chemistry, there's not 100% of anything, but I would say almost every single time, if somebody wants you to do something with molecules, they will actually write out the word molecules. So they'll actually write out the word molecules. So it is usually fairly safe in pretty much all cases that if you see MOL, again, that is again the abbreviation for moles and not molecules, which, like I said, is a very common sort of thing that people just kind of do. Now, when we talk about a mole, what does it represent? Well, it actually represents a particular number, and that number is known as Avogadro's number. And Avogadro's number is basically 6.022 times 10 to the 23. And that is basically what a mole represents. And basically, 1 mole of anything will represent that you have 6.022 times 10 to the 23 of it. And again, that's Avogadro's number. Now, obviously, you do need to know this for sure, right? Now, the deal with Avogadro's number sometimes confuses people as well is Really, the units could be anything. So, these could be atoms. These could be molecules. These could be pizzas, right? These could be shoes, whatever it might be. Although you may come across the occasional pizza shoe question, I would say most of the time, the units that you're going to use for Avogadro's number are going to be atoms and molecules. Those are most of the time the units associated with them. And what should you think of sort of Avogadro's number and a mole? You should think of it really as a conversion factor. And that's really what it is. It's a conversion factor that you could run like any other conversion factor. You could say 1 mole something over 6.022 times 10 to the 23 atoms if you want. Or 6.022 times 10 to the 23 atoms over 1 mole of something. And again, just like a normal conversion factor, you will not use it, both of them together. We use Avogadro's number basically to do this conversion, to go from moles to atoms, our molecule, and backwards. So that's sort of your conversion factor to go both ways. If you have moles and want atoms or molecules, Avogadro number is your choice. If you have atoms or molecules and you want moles, Avogadro's number is also your choice to do that. You could do Avogadro's number relationship with anybody you like on the periodic table. So you could say in 1 mole of hydrogen, there is 6.022 times 10 to the 23 atoms of hydrogen. If you want 1 mole of carbon, there is 6.022 times 10 to the 23 atoms of carbon. Each of those will give you 2 conversion factors that you can use. By the way, it doesn't matter if it's an element or a compound or anything like that. If you had 1 mole of water, that would give you 6.022 times 10 to the 23 molecules of water. Here we use molecules because water is a molecule rather than when we're dealing with an element, we typically will use atoms as sort of the unit. So that's what I was mentioning earlier. The unit for Avogadro's number changes, but the number is obviously the same. Any questions on that there? Okay. So as I mentioned, the mole represents 6.022 times 10 to the 23. And again, just like if you had a dozen of something or a dozen oranges, you would know you have 12 oranges. Now, probably the most important sort of conversion factor that we use and that you'll use the most is molar mass. And to be honest with you, you'll use molar mass more than you'll use Avogadro's number. Molar mass is really the starting sort of calculation for a lot of calculations that we do in chemistry. It's our ending of calculations as well. So molar mass, like atomic mass, is basically the mass of a mole of something, and it has units of grams per mole. So when you calculate the molar mass of something, you can calculate it in how many grams there is per mole. Typically, the number stays with the grams part, and it is 1 mole of whatever you're looking at. So, for example, we can find molar mass from the periodic table. And if we go to carbon, that is 12.01. It is the number that we find on the bottom, which we just talked about, is the atomic mass. And the molar mass is the exact same number. So the molar mass of an element is the same in grams per mole as it is in AMU per atom. And it's Avogadro's number, by the way, that kind of gets you there. So we could take from the periodic table for carbon and say there are 12.01 grams of carbon and 1 mole of carbon. That will give us a molar mass of carbon of 12.01 grams per mole. And once again, the number typically stays with the grams and is per 1 mole. You could really use this as a conversion factor. You could flip it around if you needed to. and do some dimensional analysis. Moles on top, 12.01 grams on the bottom. You could do that from anybody on the periodic table. Hydrogen 1.008. That means there's 1.008 grams of hydrogen in a mole of hydrogen, giving you 1.008 grams per mole as the molar mass, or if you want to use as a conversion factor, mole on top, 1.008 grams there on the bottom. You can use it either way, doing dimensional analysis. If you were asked what is the molar mass of carbon, you would write it this way with the grams on top per mole. And if you were asked what the molar mass of hydrogen is, you would also write it like this. By the way, we could do molar mass for things that are not just elements, but are molecules or compounds. So if you had water, you basically would go to the periodic table and you're basically just going to add up all the parts here. So we can see that there are two, as the number goes to the guide to the left. There are two hydrogens, so 2 at 1.008 grams per mole, plus our one oxygen at 16 grams per mole. And that makes up our basically H and O's, right? Two H's and an O. And that gives us 18.02 grams per mole is the molar mass for water. So if you need the molar mass of something, you're basically just going to add up all the parts from the periodic table. And once again, you could also use this as the other way if you're going to do a dimensional analysis conversion. Moles on top, 18.02 grams on the bottom. But once again, if you were asked what is the molar mass of water, 18.02 grams per mole is basically the answer that you typically would give. Molar mass is, again, like I said, probably the conversion that you're going to use the most. And it is the conversion factor that allows you to go from grams to moles or moles back to grams. So that is definitely the molar mass that allows you to do those conversions. And those are two conversions that you do a lot in chemistry, going from grams to moles or moles back to grams. And in the same problem, you might do both, go from grams to moles, and at the end of the problem, go back from moles to grams of something else. And it is a very common sort of calculation that is used. So numerically speaking, the AMU per atom and the grams per moles for each of those elements are the same. And as to the earlier question, definitely for molar mass, 4 significant figures is the general rule of what you want to pull from the periodic table and use in your calculations. Or if you're just asked to calculate molar mass, again, 4 significant figures is typically the number that you use. Here's a relationship again between AMU and grams. You don't have to derive it or anything like that. So we're just going to go through this here. So as I mentioned before, Avogadro's number and molar mass are used to do those type of conversions. Now, I will say that the relationship between molar mass and Avogadro's number is this. If you have, for example, 1 mole of hydrogen, that would be 6.022 times 10 to the 23, 23 atoms of hydrogen. And that would have a mass of 1.008 grams. If you had 1 mole of water, that would be 6.022 times 10 to the 23 molecules of water. And that would have a molar mass of 18.02 grams. So the relationship is that if you need to go from grams to moles and moles to atoms or molecules, that is Avogadro's number to get you there, and that is molar mass to do that. If you need to go backwards from atoms to grams, again, Avogadro's number to moles, molar mass to take you the rest of the way. People learn Avogadro's number and they want to use it in every calculation they ever do, and you definitely should not do that. So here's the deal. If you do not hear anything or see anything in the problem that mentions atoms or molecules or asks you to solve for atoms or molecules, you should leave Avogadro's number on the side. You should not use it. Now, if it mentions something about atoms or molecules, either they give you a number that's in atoms or molecules, or they're asking you to solve for something in atoms or molecules, then somewhere along the way you're going to be using Avogadro's number. But that is, again, a very common error. People just want to use it a lot in all the calculations. The good, bad use of that is sometimes people will use it up front in the calculation and multiply and then divide it out at the end, which is a good way to do it wrong, but it corrects itself. But again, if you don't hear atoms or molecules, don't use Avogadro's number. If you do, then somewhere along the way you got to use Avogadro's number. Any questions on that there? All right. All right, so why don't we try one here? How many moles of helium are in 5.46 grams of helium? Take a few moments there and see what you come up with. Okay, so we take a look at this, and the first thing is we're looking for how many moles are there in 5.46 grams of helium. So the first question is, do I need Avogadro's number here? Answer is no, because again, there's no mention of atoms or molecules. This is a simple conversion between grams to moles. And again, it is the molar mass that allows us to do that. We would go to the periodic table and look for helium. And underneath helium, we will see 4.003. That's going to give us really the conversion factor we need. That basically tells us that there are 4.003 grams of helium in 1 mole. That's going to give us our conversion factors of the molar mass, 4.003 grams per mole, or if we needed to, moles over 4.003 grams. So we're just going to set this up dimensional analysis here. Opposites cancel. So we're going to go 5.46 grams of helium. Again, grams of helium up on top to get rid of them. We're going to go opposite location with the grams. That's going to go 4.003 grams per mole of helium. Again, we're going to multiply and divide because we're dimensional analyzing this. Grams are going to cancel. Going to yield us a 1.36 moles of helium. I will say in terms of sig figs, probably that number is the one you want to look at there in that particular case. Any questions on that? Yeah. From the periodic table. What's that? It does. So some will have 4.003, which is really a common number, 4 sig figs for it. Again, some periodic tables are around. If you look at the periodic table up there for hydrogen, 1.01. Most will have 1.008. Some will have 1.00 and a bunch of numbers as it as well. What's that? It is. But typically speaking, when you pull the molar mass off the periodic table, if your periodic table has enough, 4 significant figures is typically what you take. Yeah. Other questions? And like I said, you do see some rounding starting to happen now with some periodic tables, but some will have a lot more numbers, some will have less. But the general rule is 4 significant figures is what you want to take it to. So obviously, if you use 4.04 in the calculation from that periodic table, you'd be fine. Yeah. Other questions? All right, so let's do this. What is the mass in grams of 1 gold atom? Again, gold on the periodic table, 197. All right, so give it a go, see what you come up with. All right, so let's take a look here. In this case, we're looking for the mass in grams of 1 gold atom. So right there, that is a keyword. Atom is mentioned. So really somewhere along the way here, we are going to need to use Avogadro's number. We do want to end up in grams, and we are starting with atoms. And sort of the thing that ties these guys together is moles. So that's sort of the center sort of piece there. So again, going from atoms in this case to moles will require Avogadro's number to do so. And once we do have it in moles, that is where the molar mass from the periodic table is going to come into play. So that's sort of our pathway here. Remember that in this case, 1 mole of gold will have 6.022 times 10 to the 23. Here we are going to use atoms because it is just an element. And from the periodic table, we could pull off there that there in 1 mole of gold, there is 197.0 grams of gold. So these are our two equalities that we can use to get our conversion factors. We're going to set it up here again, dimensional analysis approach. So we with 1 gold atom. And again, opposites cancel. So atoms are up on top. So we are going to want Avogadro's number on the bottom so that it cancels. Per mole of gold. Once again, if I stop my calculation right at this point, I am in moles of gold. I don't want moles. I do want grams. So we're going to use our molar mass conversion to take us the rest of the way. And here, moles are up on top. So when I go to my molar mass, I do want moles on the bottom in the opposite location. And my grams up on top. Again, it is dimensional analysis, so multiply the top, divide the bottom. Remember, Avogadro's number is in scientific notation. So we want to make sure we are using our exponent button here. So basically 197 divided by 6.022, exponent button 23. And that's going to get me, and by the way, the moles here will cancel, leaving us grams left over. 3.271 times 10 to the minus 22 grams for our gold atom here. In the case of significant figures, really 1 is sort of like a counted number, so really you could have went with as many sig figs as you wanted. I think I went with 4 here because of the molar mass was 4 as well. So, but basically if you had 1 as something, it would be something really counted in that sense, which would be an exact number. Any questions on that calculation? All right, let's try a few more here. Zinc. How many grams of zinc are there in 0.256 moles? Okay, so in this case, we're looking for grams and we have moles. So once again here, we do not need Avogadro's number as again, there's no mention of atoms or molecules. Remember when we see the MOL here, it is moles and not molecules. So this is again going to be a moles to grams conversion, which is going to be the molar mass from the periodic table. So we could pull it off the periodic table there, about 4 significant figures, and that will tell us in 1 mole of zinc, there is 65.39 grams. And we'll start with what was given to us, 0.256 moles of zinc. Once again, opposites cancel, so moles are up on top. So we do want moles on the bottom. So a mole of zinc is 65.39 grams. Once again, the moles will cancel and basically multiply the top there, 0.256 times 65.39. Gonna get us here 16.7 grams of zinc, 3 sig figs off of that first number. Yeah. Any questions on that there? Right, a few more here. We're looking for how many moles there are in 23.2 grams of ethanol, and also how many molecules. Some numbers from the periodic table will be helpful. Carbon 12.01, oxygen 16, and hydrogen 1.008. All right, take a few moments there and calculate it up. Okay, so let's take a look. We'll start with the first part here, which is we're looking for how many moles there are in 23.2 grams of ethanol. So once again, in the first part, there's no mention of atoms or molecules. This is really just a grams to moles conversion here. And remember our grams to mole conversion or moles to grams, that's going to be the molar mass. Again, from the periodic table is where we can get that. In this particular case, we have the formula for ethanol. So to get the molar mass, we really just need to add up all the parts to it. So there are 2 carbons, and if we go to the periodic table there, Each carbon is 12.01 grams per mole. And that's for our carbons. We will add it to our 6 hydrogens, each at 1.008 grams per mole. That takes care of our oxygens. And lastly, we have hydrogen. We have one oxygen at 16 grams per mole. And that takes care of our oxygen. This was our hydrogen. There we go. And if we do that, we will end up with, looks like 4607. And again, the units here are grams per mole. Again, the number stays with the grams part, and it's always per 1 mole. So when you're calculating the molar mass of something, it is always per 1 mole. It's also really important, for example, a common error that people make is when they see something in an equation, for example. Let's just say we had 2H2O, and they needed to calculate the molar mass for water. They oftentimes will use the 2 in front of it when they're calculating the molar mass, and you should not need that. So if you're asked to calculate the molar mass and you have something, for example, in an equation that has a coefficient in front of it, whenever you calculate the molar mass, it is based on just the formula by itself, just one of the formulas. That's why it is per mole of that formula, basically. So you should always do that. You should not do the coefficient in front, which is, again, a common error that sometimes people will do. So we'll go our 23.2 grams of C2H6O. Once again, opposites cancel, so we do need grams on the bottom, so we do need to flip the molar mass around and put our grams on the bottom so that they cancel. Moles C2H6O. Again, multiplying the top, dividing the bottom. We'll get rid of those grams, and we will end up with 23.2 divided by 4607. And here we will end up with 0.504. Here I am going to round because it is one of the answers we are looking for here. And we would end up here 3 sig figs, once again, based off of the first number. First off, any questions on that part of it? Second part of it is sort of a continuation. We want to know how many molecules there are. Now for this part, because we're looking for molecules, that should open up for us Avogadro's number, because obviously that's how we're going to get there. So in this case, since we actually have moles from the previous step, we really are just going to go from moles to molecules in this case. And once again, it is Avogadro's number that's going to sort of allow us to do that. So in 1 mole of ethanol, there would be 6.022 times 10 to the 23 molecules of ethanol. And again, that's going to serve as our conversion factor. So just continuing on with our calculation here, 0.504 moles of C2H6O. Opposites going to cancel here. So we do need moles on the bottom. So we'll go with moles of C2H6O. Avogadro's number will go up on top, and these will be molecules. The moles will cancel, and since I have it in my calculator, I'm going to go with the unrounded number in my calculator here. So this is sort of a continuation. And we're going to end up with here, looks like 3.03 times 10 to the 23 molecules in this case. Yeah. Any questions on that there? So again, molar mass, definitely one we use a lot, and don't overuse Avogadro's number. Let's try one more here. What is the mass in grams of 1 molecule of caffeine? Again, some numbers from the periodic table. Carbon 12.01, hydrogen 1.008, nitrogen 1401, and oxygen 16. Okay, let's take a look here, and again, we are looking for the grams in 1 molecule. So again, that is a key word to tell us somewhere along the way, we are going to use Avogadro's number. Uh, our sort of pathway here, right, is we have molecules. Remember, we could use Avogadro's number to take our molecules to moles. And from that point, we can then use the molar mass from the periodic table to take us to our final unit, which is grams. So we're going all the way across here. In order to do that, we do need some information. Obviously, eventually we're going to need the molar mass here of caffeine. So might as well just calculate that up front. So we're just going to again use the formula and just add up the parts from the periodic table. So there are 8 carbons, each at 12.01. There are 10 hydrogens, each at 1.008. There are 4 nitrogens, each at 1401. I'll go underneath. And 2 oxygens, each at 16 grams per mole. And if we add all that together there, looks like we're going to hit like 194.2, I believe. 0.2 grams per mole. So that's going to be really our molar mass conversion factor when we get there. Our Avogadro's conversion factor, which is what we need to open with, is just Avogadro's number, basically. So 1 mole of C8H10N4O2 is going to equal 6.022 times 10 to the 23. And these would be molecules here. So to start our calculation, we're going to start with taking our first step here, molecules to moles. So we'll go with 1 molecule of our caffeine. Again, going to go opposite, so we do need molecules on the bottom. That means Avogadro's number is going to go on the bottom because it goes with the molecules part of it. Per mole of our C8H10N4O2. If we stop right there, molecules are going to cancel. We are left with moles. We basically just got to there. We now need to go the second half here with our molar mass we calculated above. And once again, I'm just going to continue the calculation here. Seeing moles are up on top, that tells us when we use our molar mass, moles need to go on the bottom. And remember, when we calculate the molar mass, it's just 1 mole, whatever it is. And up on top will go 194.2 grams. Again, multiplying and dividing is going to get rid of our moles. So basically, so basically in this case, we're going 194.2 divided by 6.022 to the 23. And that's going to yield us 3.225 times 10 to the minus 22 grams of caffeine in this case. Once again, just kind of going to 4 sig figs on this one based off of the molar mass, as technically it'll be kind of like a counted type of number there, the 1. Question on Avogadro's number, molar mass. Definitely need to get a hang of molar mass. It is used a lot coming up, in a lot of calculations. So, like I said, grams of moles or moles of grams is a beginning or ending or beginning and ending calculation, and a lot of calculations coming up. Any questions on that? All right, before we kind of move away from this, another aspect of this, and maybe we'll just steal, this here. So let's say, for example, we had a question, and I don't know. I'll do this. 23.2 grams. So let's say we started with 23.2 grams of our ethanol, which we did in that previous problem, since we'll just borrow it here. C2H6 and 4607. Looks like. And we had our molar mass there, which was 4607. We calculated already. So we'll just borrow that. All right, so let's say we had 23.2 grams of ethanol, and we wanted to know let's do, let's see here. Let's do two things. Let's do how many grams of carbon does it contain? And also how many hydrogen atoms does it contain? So in this particular problem, we're looking for two separate sort of answers, and both of them are not dealing with the entire sort of compound, right? Here we're dealing with, in the first one, we want to know just about carbon itself. And on the second one, we're interested in just what hydrogen by itself, not the entire thing. So this sometimes comes up, and sometimes you need a way to convert from like the whole thing to maybe just one of the elements that are in that particular formula. And to do so, we could actually use the formula itself as a conversion factor. So when we look at the formula for ethanol in this particular case, when we look at the bottom numbers here, the 2, the 6, and the 1, these can be represent the moles of each of these elements. So from this particular formula itself, we could actually get a number of conversion factors that we could use. So for example, we could say in 1 mole of the entire thing, there would be 2 moles of just carbon, and that 2 is coming from the little subscript on the bottom. We could also say that for 1 mole of this entire thing, there would be 6 moles of hydrogen. And we could also say for 1 mole of this entire thing, there would be 1 mole of oxygen. So these are sort of 3 equalities we could actually get from the formula itself. And from each of these equalities, we could use 2 conversion factors if we needed to. So with that information, that is what allows us to answer this type of question. So for example, the first thing we would want to do is we would want to convert these grams of the entire thing into moles. And the reason we want to do that is all these conversion factors we just came up with, it's all about moles, so we need them to cancel out. So we're just going to steal what we did on the previous problem where we did that conversion. So we're going to convert it into moles, and we've got 0.504, it looks like. So we're going to use the molar mass just like we did on that previous problem for the entire thing. And 0.504 moles of the entire thing. And again, we do have to kind of do that conversion so that we could use our conversion factor that we just came up with. So now that we have moles of the entire thing, we could first tackle our carbon. And I could take the moles of the entire thing. And now I could use that relationship from the equation and figure out how many moles of carbon there would be. And once again, opposite's going to cancel. So 1 mole of the entire thing would give me 2 moles of carbon. If I did my normal dimensional analysis, multiplying the top, dividing the bottom, the moles would cancel. And if I stopped right at this point, the unit I would be in is moles of carbon, right? And that, using the actual formula as a conversion factor, allowed us to go from the whole thing to just the carbon element in there. But this is actually not what I'm looking for my question. I'm actually want grams of carbon, right? So in this case, we now have moles and we want grams. So that is the molar mass of carbon from the periodic table. Again, not the molar mass of the entire thing, because at this point we are dealing with just carbon. So we want to use the molar mass of carbon, which, as we saw previous problems, 12.01 grams per mole is the molar mass of carbon. And we are going to use the grams up on top so that we end up with grams, and it's going to be a mole of carbon. Once again, continue to multiply and divide. Moles of carbon will cancel. We're now left with grams. And that will tell us that, again, if we use the rounded number from the previous problem, 0.504 times 2 times 12.01, and we got in the ballpark of 12.1 grams of carbon in this particular case. Questions on that calculation? Now we could also do the second calculation here, which is we are interested in how many hydrogen atoms there are in this. And now the deal on this is I am looking for hydrogen atoms, which tells me Avogadro's number needs to be involved in this calculation. So I'm going to still start with my moles of the entire thing that we calculated previously. But now I'm going to go to moles of hydrogen in this case, because that's what I'm interested in. And I'm going to erase my little arrow there that's kind of in there now. So looking at our relationship from the equation, we could see that for every 1 mole of the entire thing, we're getting about 6 moles of hydrogen. So 1 mole of the entire thing here will give me 6 moles of hydrogen. If I stop my calculation right at this point, I'm in moles of hydrogen, which once again is not what I'm looking for, but I am looking for atoms of hydrogen. And now this is where Avogadro's number is going to come into play. I can now do Avogadro's number on the back end, and we want a mole of hydrogen will be 6.022 times 10 to the 23 atoms. Multiplying the moles will cancel, going to leave us atoms left over. And we'll use our rounded number 0.504 times 6 times 6.022 to the 23. Going to get us a 1.82 times 10 to the 24 atoms of hydrogen. So this is a type of problem that you sometimes come across where they're really not interested in the entire sort of formula or compound. They may just be interested in an element that's in it, like carbon, hydrogen, or oxygen. And you could use the actual formula as a conversion factor. And those numbers on the bottom can be considered the number of moles, which, as we'll talk about in the next part of this chapter, is how we calculate formulas like molecular formulas and empirical formulas as well. Any questions on that part of it there? All right. I think it's actually a good place to lay it up there.